One of the ways we split up mathematical models in the last video was whether they were analytical models, where the model is based on a deeper understanding of the processes involved, or empirical models, where the basis of the model comes from real-world data. In this video, we want to have a closer look at empirical models, which form an almost essential tool in early system design, and one application in particular, when it is a matter of estimating the cost of a project.
What we're hoping for are what we hope will be simple relationships between two parameters, one of which we know and the other we want to know. Because we are dealing with parameters, they're normally called parametric models. The approach is extendable to cases when there's more than one input parameter, but mostly we use one input and one output. Now, all we need are these functions. If we have these relationships for all the important system parameters, then we can speedily produce preliminary design, feasibility, and preliminary system outline purposes. For example, if the function of a spacecraft power system is to provide 1 kilowatt of power using an array of photovoltaic cells, then we can use these relationships to give us estimates for the solar array area. It comes up 4.8 square meters, and the mass of 8.5 kilograms, all from the known power level. Another example is we can make a first estimate of the mass of a satellite structure as being 6% of the total mass it will be required to carry. Most of the time we don't even think that these simple rule of thumbs are parametric estimates. We say our solar arrays normally give us 8.5 kilograms per kilowatt, or structures run at about 6% of the spacecraft mass. But parametric estimates are what they are. As you can appreciate, with a set of such simple rule of thumb mathematical relationships, an initial system design can be built up without the effort of going into unnecessary detail, confident that when we reach the detailed design stage, the elements will fit together within the budgets we set at the start. These parametric models are often created within design companies. They're generally empirical relationships based on the company's previous products and experience. This means that all the factors related to the manufacturing within the company are included in the function.
This is one of the important advantages of empirical modelling. Because they're based on the real world, they should cover all the factors that go into the relationship, even factors that we're not really aware of. As long as we stick to designs that are not too different from past experience, these parametric models can then be incorporated into company design guidelines, which of course are commercially confidential. That is one of the reasons large aerospace companies dominate and new companies find it difficult to establish themselves. In just this historical knowledge that the older companies can draw on to support their system design work.
But sometimes these simple parametric rules of thumb do slip through to the public domain. In the space industry, most famously in this book, Space System Design and Analysis from Jim Wirtz and Wiley Larson. It goes through all the rules of thumb needed for a small satellite. And indeed, when it was first published in 1991, it opened the door for several new small satellites from new players, often from countries that had not made satellites before. Here is an example of the sort of thing you'll find in it. These are graphical parametrics that give power and mass estimates for two types of power amplifier that are used in satellite communications. Now, one type, solid state, uses more power but weighs less than the alternative travelling wave tube amplifiers, and the parametric allows the designer to do a trade-off to establish the best systems level option. And here is another example from Wirtz and Larson. And this is as simple as it gets. If you have a function, in this case they are all related to attitude control, then here are estimates of mass and power values that go with that function. In this video, we want to concentrate on one specialist but important empirical modelling technique, parametric cost modelling. A few times through this course, we have casually mentioned costs as a key decider in the process, such as here in the requirements capture video when working through the logic of the concept design phase. We introduced a decision centred on cost of the feasibility design without explaining how you would know the cost of a vague concept design when you do not even have a detailed parts list. Another example in the life cycle video, we mentioned that something like 5 to 10% of the total project cost should be invested in the feasibility design and 10 to 25% in the project definition stage. This was something that was recommended as far back in the 1960s in the Downey cycle. But that gives us a problem. How do we know what the overall cost of the project is going to be when we're at the very beginning of a new design?
Actually, knowing the probable project development and production costs is not just important to assess whether there's been adequate investment in the early stages. We've already seen it's important to inform the financial decision makers as to whether to proceed or not and how much money to start allocating. Here are 4 reasons, though, why establishing costs from an early design concept is important. You need to know how much you should spend at different phases of the project. You need to be able to give your financiers some reasonable idea how much money you're going to require. You need a way to understand the financial impact of technical decisions. And in due course, when you start to bring your subcontractors on board, you need to have an independent idea of what their costs are going to be in order to stop them taking you for a ride.
But the question is, how do we estimate those costs?
Let me try to show you that you're not as ignorant about costs as you think. Perhaps you've seen this. It's a project started in the United States to develop a small supersonic business jet by a company called Ariane. It's designed to take 8 to 12 passengers up to 8,800 kilometres at a cruise speed of about Mach 1.4, avoiding supersonic bangs by clever design. Its operational weight empty is 32 tonnes, to give you an idea about its size. Now, if I told you that you could develop this aircraft for $100 million, what would your reaction be?
Well, we have difficulty making a new small satellite for that, and I know that it's costing twice that to integrate existing bombs and missiles to the UK's F-35. So I would think that's probably a little low.
Okay, so you have some idea about what these things cost. Now let me suggest a higher number. Suppose we said 100 billion.
Well, Concorde cost about $30 billion in modern money, so I would think that's a bit high. After all, although it's an advanced aircraft, it's not that large.
Right, that gives us a fairly wide range. Let's try something in the middle. Say between $1 billion and $10 billion.
Well, now don't know. I mean, somewhere in that region, possibly. But...
Well, let's start with what you were doing, comparing the cost I was giving you with costs that you already knew. You are using a very rough parametric model. So let's just look at what a more sophisticated parametric cost model can do. We know what kind of numbers we had last time, and we know that size has an effect. And a lot of engineering cost estimate works this way, by finding out what it cost last time and asking, how does this time differ from last time? Let me switch then. Instead of asking about the development cost of airliners, let's look at the production cost. Or rather, let's look at the flyaway price, since airliner manufacturers are hesitant about giving away what their actual costs are. I'm assuming that there is some sort of link between the two, although I know that the price is always negotiable. That said, here is a chart of the 2019 prices for the current range of Boeing airliners. You'll notice that there is some sort of trend. But of course, other companies make airliners, so let's put Airbus prices in as well. You'll see that they fit fairly well on the same graph.
Oh, wouldn't they have to? Otherwise they wouldn't stay serious competitors. And also, aren't there a lot of questions about government subsidies?
You're right, of course. There's pressure on each of the competitors to keep their prices competitive. If you can't keep your price about the same as your competitor, then you've either got to have some sort of magic ingredient, which are called unique selling points, that makes the price difference acceptable, or you'll be foolish to go into the business at all. And the fact that the price has some flexibility in it allows you to negotiate with your customer. But there's one fundamental commercial law that you need to take into account. If you're going to remain in business, the price needs to be larger than the costs.
And commercial competition would tend to keep that difference small.
Exactly. Now let's look further. While Boeing and Airbus make by far the majority of civil airliners, they're not the only people who build passenger jet aircraft. There are business jets and regional airliners. Let's put a few of those into our chart. Now you will see there is a different price range, but interestingly, they fit on roughly the same curve.
But you are using log-log graph, so doesn't that hide some of the scatter?
I didn't say it was perfect, and doing that allows me to put in different sorts of aircraft on the same chart. Another reason for using log-log is that I seem to be getting a straight line correlation. Let's actually give numbers to that line. Because it is a log-log graph, it's actually a power law relationship, but the exponent is 0.93. That's nearly 1, which means you're not too far off a curve that says you buy airliners by the kilo, like bags of sugar. So where does Ariane fit relative to this curve? This is their current estimate. In this case, it is not on the curve. It is almost exactly a factor of 2 higher. But remember, this is a supersonic passenger airline, travelling at about twice the speed of the other subsonic jet aircraft on the chart. You might expect it to be more expensive, and Ariane will argue that because of its higher speed, it will have more productivity than a subsonic jet. You must not imagine that everything will fit on a single curve. You have to compare like with like. What I have shown are all current airliners, but for many of the things that we use in parametric analysis, we need to go further back in time. As we pointed out in an earlier video, some years can elapse between the original proposal for a major project and actually building and launching it. So the examples you use in predicting costs are going to go quite a long way back in the past, and may not even be using the same technologies. Won't that make a difference? Let us add a similar set of data on airliners dating from 1983, after correcting for inflation, and see how those fit on our curve. They're not the same set of airliners. Some have gone out of production and a few new models have appeared. So I'm saying that airliners cost just as much a kilo today as it did 38 years ago. That is, over that time we haven't got any better at making aircraft. Well, of course, there are a lot of changes which involve not only new technologies in the airframe, but the introduction of computer-aided design, some more challenging safety requirements, and increasing real value wages in the industry. Actually, I cheated a bit here when considering inflation. We often think of inflation as a single figure, and normally we're thinking of the Consumer Price Index. But in fact, there are many inflation indices, and which you use depends on what question you're asking. What I used here is an official aerospace inflation index. And how do you get that? Basically by comparing the price for similar products from the industry at different times. The aerospace inflation is another empirically derived function, so it will cover all those factors like technology changes. So the overlap we see here is not too surprising. But the aerospace inflation index is actually not too far from other measures of inflation, so in the end, all those factors are probably lost in the noise.
So when generating a cost parametric, we need to have the inflation rate for the industry from which we're getting the data.
Yes, that's right. But once we have the data, we can then use the curve fit to derive a formula that takes us the form shown here. These relationships are called cost estimating relationships, or CERs, and generally turn out to be in the form of a power law. The parameter used to derive the cost is normally, but not always, mass.
Hey, where did you find this?
It locks under my seat.
Are they heavy?
Yeah.
Then they're expensive. Put them back.
The constant and the exponent are derived from best fit to the available data. The The exponent ought to lie between 0.3 and 1, and there's a kind of logic behind this. If the exponent is greater than 1, it means that a larger version of the same thing would be more expensive per kilo than the smaller one. And this sounds unlikely. You buy the giant box of washing powder at the supermarket because it's cheaper, right? At the other extreme, if the exponent is less than about 0.3, then you're probably not going to get a good correlation with size. And however you choose to define it, and that may mean you need to look at some other factor. However, there are other factors which lead to expectations about the value of the exponent in the cost estimating relation. We saw that the exponent for production aircraft was 0.93, and for production items we would expect an exponent value in the upper part of the range, like this. However, development programs have a much weaker dependence on size, with exponents closer to 0.5. The constant in the equation is based on examples that you already know about. This means that we really ought to know what those examples are when we come to assess whether this example is going to be easier or more difficult than last time, which is what the second technology factor is about. This is a problem with certain commercially available software packages which will offer to evaluate this technology factor, but don't provide reference examples to compare with. There is no law of physics that states that the cost has to be on the parametric curve. But if it isn't, then you need a good explanation of why this case is different. The technology factor may include considerations of such things as materials and processes used, complexity of the design, the environmental challenges that the product will have to meet, and so forth. Sometimes we may use new materials like carbon fibre to replace older materials like aluminium to save weight, but the technology involved may make the product more expensive. It is not always true that lighter makes cheaper. And finally, there is software, which is a case where size based on mass cannot apply, and which we know rather than costing nothing can cost a great deal. And there we have to go into a whole new way of defining size.
So, different technology factors enable us to explore the cost implications of using alternative technologies. But it has its limitations. You can't continue to keep upping the technology to make things lighter and hence apparently cheaper.
Absolutely. The technology factor is another empirical factor. If you've got no information on the technology you want to use because it's too new, that you do not have any cost estimating relationship, but maybe in that case you need to have an early technology development program to establish some data points.
Well, that may be obvious, but I'm also seeing the reverse argument that by simplifying the technology we can massively decrease the cost. And surely that's not always the case. Most of the cost of making a product, whether a part or a complete system, is in producing the design, the drawing, the analysis, the testing, and this takes the same regardless of what you make it out of, or the technology that you are using.
But in that case, you're not simplifying the system or the processes by which it's made. You need to know what you're doing. I have an example from work done by Kistler in trying to make a low-cost launch vehicle. One of the things they did in the designing the propellant tanks was to increase the stress safety factor from, talking from memory, 1.4 to about 1.8. What that did was to eliminate the need of critical crack size inspections on the structure, massively reducing inspection costs, although the mass did go up somewhat. Kistler got a lot of the engineering right. What killed him in the end was the assessment of the market.
Take another example. When we were proposing Inmarsat 2 in 1984, we did not actually use CERs. What we did was a process called bottom-up costing. So I think we should quickly look at that. With bottom-up costing, you first need to create a complete design and a corresponding work package structure for the whole project, giving in detail all the various activities that will be needed to complete it. And you also have to identify who's going to be responsible for each activity. And then you ask the individual work package managers to cost their individual work packages. Then, when you have all those, you add everything up and you have a bottom-up total. But there is a problem in that you can't get a bottom-up total until you know in detail everything that you're going to have to do. But you have at least made the work package managers responsible for the costs of the things that they are going to do. Another problem is that it is expensive. There are thousands of work packages, and even if each only takes a couple of hours to cost, that still costs in total hundreds of thousands of pounds to do a complete estimate. For British Aerospace, Inmarsat was their first commercial satellite bid, and they invested around £2 million in the proposal, and it was clear they could not do this every time they competed for a contract. It is also not only more expensive, but even at best no more accurate. First of all, you have to ask, how do those work package managers come up with their estimates? Well, what they do is they look at what it cost last time and interpolate or extrapolate, depending on whether they see the job as bigger or more difficult or perhaps even easier. So the end result is still an empirical parametric. And then if you hope that the bottom-up estimate and the top-down parametric estimate will come to the same number, well, they probably won't, because the bottom-up estimate is a plan to deal with all the foreseen problems, while the top-down estimate, being based on past experience, also includes the extra spend for those unforeseen problems that you particularly get in development. Now, you can get around this by adding a contingency factor to your bottom-up estimate, a little like adding a margin that you put on mass estimates. Again, this will be a contingency factor that's based on past experience. And more often than not, this will just be a subjective opinion from senior management, not particularly based on any hard analysis of past successes and failures. A further difficulty comes when you have subcontractors, and in this case essentially all the work package managers are now effectively subcontractors. How do you trust what they say? They of course will be making their lives easier. Or if they are real subcontractors, they'll be making room for bigger profits. Now, the traditional solution was to ask for competitive bids, but this may not always be possible. And finally, there is a phenomenon that a director Bob and I once worked for pointed out. He said one way of pushing the cost of a project up was to ask for a re-estimate, because nobody's going to take things out of their bit, but somebody will remember some things that they left out but ought to have included in the first place, and so the cost goes up.
It was the promise of lower bidding costs and a more accurate estimate and the ability to quickly cost changes and hence iterate and optimise the design that led British Aerospace to adopt cost estimating relationships for its bids after Inmarsat. This was in the mid-1980s, and by then cost estimating using parametrics had evolved into a reasonably mature presence from its origins in the 1960s, when several researchers independently started working on this idea. Cost parametrics can be used at the equipment level, giving cost estimates for the system components by component. This suffers from some of the same problems as conventional bottom-up costing, in that you need to have a very detailed understanding of the system and components to do it. Probably more detail than you really needed at this stage. The problem is that such a large amount of design work is undertaken without any cost guide except the good judgment of the engineers. And like bottom-up costing, by the time you reach that point it is too late and too expensive to iterate the design. The next level is to cost at the subsystem level. This requires less detail in the design, although a good feasibility study should be assembling realistic assessments of the size of the subsystems required. Subsystem estimates should tell you where the expensive bits of the design are, and in cases where novel technology is involved and where the parametrics become simple guesses, it at least brackets the uncertainty to just a part of the total system cost. It is also a level where the system team can do the costing without involving the subsystem departments and potential subcontractors. Finally, We can cost at the system level using the estimated mass of the complete system, which is what we were doing when we looked at Ariane. Proponents of this level of parametric analysis argue that if you base the costing on subsystem level parametrics, then anything you've left off will not get costed. System level parametrics are less sensitive to these errors. Also, system level parametrics covers real world factors like mistakes, project slips and so forth. As a consequence, system level parametric estimates provide a sanity check on estimates laid at a lower level, which is what we were doing at the beginning with the Ariane project. However, on the downside, if you use system costs, you do not account for any changes in the technology, innovative system design, etc. And in fact, there is no way to cost improvements, often the very thing you want to base your new system on. Unlike budgets of mass, power and so forth, where summing all the equipment values gives you the system total, with the subsystem level cost estimates, simply adding together all the component cost estimates based on mass or size will not do. There are other program costs which come on top of those costs. These are things like system engineering design, assembly integration and test, and management and project administration. The cost of these things is generally related to the cost of the components they bring together, and as a consequence we refer to them as wraparounds. This diagram shows the structure of the system cost model for HOTOL, and you can see that the wraparounds at the vehicle and overall system level. Because it's concerned with developing a new vehicle, the cost model must also break out the costs of system level testing, building prototypes, providing jigs and tools for the production line, and providing support in the form of ground support equipment, facilities and spares. These not only drive up the total cost, but drive up the cost of system design and management, which wraps around the whole thing. These wraparound costs are not insignificant. On a spacecraft project, the wraparounds on production costs can be as much as 1/3 of the total, and for a new development account for even more. Did I ever tell you about how I saved 150 million in an afternoon?
No.
This was back in the late 1980s when we were developing the studies on what would become Envisat at that time, the Polar Platform. And the job had gone down to Bristol, but for the first time we were getting estimates in from our potential subcontractors scattered across Europe. And the whole team sat together one afternoon to look at these and see what we got. We knew it was going to be expensive, but when we added the numbers together, it was rather more expensive than we had expected, which was going to be embarrassing because we'd been telling our lords and masters that it was going to be this price.
Based on your parametric costings?
Well, based on something at least. And fortunately, I'd done a parametric estimate at the subsystem level of what we expected the thing to do. And I could compare what we were getting from our subcontractors to what I thought it was going to be, and we could see where the differences were. Once we established where the differences were, then we could go back into what the subcontractors actually bid and discover that there were a whole series of overlaps where people had said that they were going to do the same thing as somebody else that the job was going on to. And that, in the course of an afternoon, reduced the price by 150 million euros. No, it was in those days ESA accounting units.
Did they give you a commission on the saving?
Unfortunately, it doesn't work that way.
Let us look at some more recent examples of parametric costing in operation. This is a study I did as a proposal for what we should build after the International Space Station. I called it PIA for post-ISS architecture. The idea was to develop a small station and then build as many as are needed to get the required capability. For example, it would take 4 stations to match the current International Space Station. It was based around just 3 modules. For comparison, the International Space Station has 15 pressurized modules plus additional external structure. The aim here is to minimise the design effort, and in a further strategy to do this, all three modules include the same utility module that contains the functions that they have in common. Of course, we have mass budgets for all these modules, and so we can parametrically cost them. And we can see each module costs for both development and production of both a 4-station and a 5-station architecture, the additional 5th station being for a lunar orbit base. Notice, in addition to each module, there is also the system wraparound costs, and you can see the total cost of acquiring a 4-station architecture is about $12 billion. It's difficult to establish what the equivalent ISS cost was historically because it was so complex and spread in so many countries. But the equivalent single station in theoretical terms, well then we're looking at roughly 15 to 18 billion for development and 5 billion for production, a total of over 20 billion. So we're looking here at almost halving the acquisition costs. A more recent study is the Scorpion space transporter, designed to carry people and cargo to anywhere in space between low Earth orbit and Mars orbit. The key technology that makes this happen is a nuclear engine called the Serpent, designed by Alan Bond. It is an advanced thermodynamic cycle that increases the performance of conventional nuclear rocket engines by 50%, and this extra performance is essential to meet the Scorpion's objectives. So once the technical design was complete, and of course it was time to cost the vehicle, so the mass budget was handed over to Bob. When it came to costing the Scorpion, this gave you some trouble, particularly with the Serpent engine.
It's basically the nuclear reactor, and it's characteristic of the sort of problems you can get into and how we get out of it. If you go onto the net and try and find costs for nuclear reactors, there's not good information. You get a little bit of information for nuclear powered aircraft carriers.
Yep.
and large power stations, but it doesn't really fit anything. You know what sort of ballpark you're in, but the nuclear reactor itself is only a little bit of the total thing. So this is where intermediate level costing works. Because you can take all the other bits that you know about out, cost those with some certainty, and you've got this bit you don't know about, which is a lot smaller than it used to be, sitting in the middle, that you've got to take a risk about.
Yeah, but the point is, if you haven't made a space-based nuclear reactor of this type before,
You have no idea.
you can't use a parametric model because
That's right.
Yeah.
So you're guessing.
Yeah. On the other hand, my earlier study on the post-ISS space station, that was much easier to cost because it had just existing technologies, which you
Yes.
knew well, and you costed things like that before. And having that secure estimate means I was able to argue the advantage of shifting the emphasis from design into production. Which brings us to a key aspect of production estimates, which is called the learning curve.
Right.
So returning to the Pier space station concept, if we look at the cost per station, we can see that as we make more stations, each station gets cheaper. Now in part, this is because the more you make, the more you can spread the design and development costs. But if we look at just the production costs, we still have a cost reduction. And that is because of learning factors. We have seen that the production cost parametrics are designed to give the value for the first theoretical unit produced. That is, if you make one unit, then that is what it will cost. But if you make another unit, will it cost the same to produce? No, of course not. As you make more and more units, so the cost of producing each one will get less, and this effect is called the learning curve. The mathematical model of this learning effect on production was outlined by an American Theodore Wright in the mid-1930s, and he was looking at aircraft production, although in fact it applies to all industries. So what causes the cost to drop? Well, the first thing, as the name implies, is learning. Wright did not actually invent this concept. It comes from original insights that came from psychological experiments. Psychiatrists were measuring a human's ability to learn by repeating action from the end of the 19th century. Well, it turns out that organisations also learn as they repeat activity, and if they get better at making something, it means it is also going to get cheaper. But learning is not the only reason why cost drops as production increases. So the learning curve is actually about more than just learning. If you know you're going to make more than one of something, then you make preparation. If I was making 10 of something, I probably would put some effort into making some jigs and guides, which I would not do if I was making just one. Now, if making 100, I might invest in special tools. And if many thousands, I might consider a special production line with increased use of automatic machines. And beyond that, maybe even a special factory. Another way production costs are reduced is by speeding up the time by making several at the same time. So because I am going to make a whole batch, the setup activity to get ready to make them is reduced. And finally, if you're making a large number of something, then you'll become a good customer to your suppliers, and then you can negotiate good deals. So bulk buying and other scale economies will also contribute to production cost reduction. The learning curve is described by this equation, which gives the cost of making n units if you know the first unit cost and the factor s, which is called the learning curve slope and is the percentage reduction to the average cost when the production run is doubled. Well, we already know where we get the first unit cost from, but what about S? Well, this is another factor we get from empirical observation of real life, and it's not a single value, but typically it will lie between 85 and 95%. Wong, Inverse and Larson suggests that for aerospace production, for units less than 10 units, it should be something like 85%. For 10 to 50 units, it will drop to something like 90%. And if you're making over 50 units, then it will drop to around 85%. And you probably won't come too much harm with that advice. Now, the faster rates of cost reduction predicted by this reduction in the value of S is because of the investment in tooling and automation that become viable with larger production volume. You can see the impact of learning curves in these two graphs, which show the total production cost and the cost per unit for the first 16 units. Now, if you are only making 16 units, then S is going to lie somewhere between 90% and 95%. But even then, we see the production cost per unit will have dropped by a quarter. Now, you can also see where the 85% line is heading if you're actually in production runs over 50. At 100 units, the production cost is a third of the cost of 1 unit. If 1,000, it is down to a fifth. And if you make 1,000,000, then it is down to 4%. Now, these results are of immense importance in economics. A small volume producer is always going to be at risk of being squeezed out of business by a larger volume producer. I think this impact of the learning curve on economies is tremendously important. It is the improvements in productivity that the learning curve allows if you get bigger markets, which is the whole drive towards globalization and why there's a constant striving for bigger markets and why these big dominant global companies succeed, because a little company has not got the learning curve to enable them to compete.
Why trade is worthwhile, why we shouldn't make something that somebody else can make in exchange for something that we can make in large quantities and sell to them.
Yeah, the whole drive to free trade. And of course, if you get protectionism is an acknowledgement that your smaller market and your industry in the smaller market is not going to be able to compete with a larger market coming in. So you put a tariff barrier up to counteract the learning curve effect.
but in general, trade improves the economy because you're getting larger quantities if you've got your balance right.
Yeah.
And this goes back as far as ancient Greece. I was always impressed by the fact that the Greek philosophers, who were presumably talking about the secrets of life, the universe and everything, were actually interested in trade.
Yes, and Roman Empire even more so.
Yes.
The whole of the Roman Empire lasted for, was it 3-4 centuries? And I don't know whether they appreciated it at the time, but it was the impact of trade. And when they went into Britain, many people in Britain were wanted the Roman Empire because it then gave them access to
a
the
big
markets
market, yes.
that the Romans had. There's another point in it that comes out of that graph I just showed, which is that if you get to 1 million units, you're down at 4% the cost of 1 unit. Now, you've had in your past life a little bit of experience
Yes.
where you are making 1 million
Yes,
units.
this is always interesting. That what does it look like at 1 million units? Because nowadays I'm interested in if we get 5, we've got a major production run. And I was involved with Royal Ordnance factories and making of things like shells. And it was one of the things that impressed me that this is not always designed into the system. It's the people who do it change their behaviour as well. And the particular example that's burnt in my memory, where I went round a shop that was doing forgings, forgings of shell cases. What you do here is you have a preform that you heat up in a local furnace, red heat. You put it in a mould. The mould, the centre part of the mould comes down, bang, instantly forges into the shape out, and you hoik it out and put the next one in.
Yep.
Except that the guy I was watching wasn't doing that. What he was doing was that he brought the red hot preform to the machine and put it on the side while the thing was in operation. And then as he pulled the forged piece out, he knocked it and it fell into the right place, and the next one could go while he was putting the previous one away. So he was actually doubling his productivity. He was on piece rate, so it was good to him. But it meant that machine was producing twice as much as it would have done in the original design.
But the other interesting thing there is that's an example of the learning bit of the learning curve. How many machines are involved in making a shell case?
Oh, quite a lot, yes. It's the bit that Adam Smith things. You break it up into little bits, and there's a throughput. That guy was working on that machine, and then somebody else will be working on the next bit of the process all the way down. Yes.
And each machine is specific to one specific
And
task.
you make machines specific if you've got enough.
Yeah.
And there's a trade-off between what you invest in the machine and how much it improves your productivity.
So you might be able to make a shell case on a normal lathe, but
Oh,
if you're making
definitely
1 million, you don't. You have
that's right.
one lathe does that, another lathe does
Yes,
that, another
yeah,
lathe, and they're
yeah.
all specialist lathes for the
That's
job.
right.
Yeah.
We should finish up with a summary of the points to be careful of when using the CERs. The first danger is of using parametrics outside of the range of the data. These relationships will not cover an infinite range. An interpolation between data points within the range covered by the data will be safe, but great care should be taken when moving outside that range. It can work. We saw that much smaller business jets follow the same parametric derived from larger airliners. But it does not always work and cannot be relied upon without support evidence. The second risk is using a parametric that is derived from a different technology. A statistical parametric will refer to a particular technology base or level of difficulty. It is important to determine that what is assumed in the system design is the same as the technology base used in the parametric, which is what the technology factor is about. So make sure you're using the right one. A related problem, and the worst limitation of using parametrics, is the one we've discussed with the serpent engine on the Scorpion. Parametrics cannot be used for new technology. A statistical derived parametric will of course relate to the level of technology and methods of design and construction used in the examples that provided the data used to derive the relation in the first place. But often in a new system, or simply in a new approach, it is the new technology that's the key feature, and this will have to be evaluated by other means.
The economic impact of what we create is at the heart of all engineering. One of my favourite definitions of a good engineer is somebody who can make for 50 cents what any damn fool can make for $1. So we need the tools to continually assess the cost impact of our engineering decisions.
And cost-estimating relationships are the best tool we currently have to predict the cost of our proposals. While they require a fair bit of work to create, if they're used properly, they provide reasonably accurate results, typically within 15%. And they're flexible. They're able to be used at every level for helping engineering decisions, for planning project budgets, and sanity checking the quotations we get from our subcontractors.